Okay, in this lecture we're beginning a new topic, and the topic that we're going to start is that of mathematical transforms. This is an extremely useful area of applied mathematics for engineering. It's useful because it allows us to visualize, well, it allows a couple of things. First of all, it allows us to solve what might otherwise be very difficult problems to solve, if not impossible problems to solve, by taking some transformations of a problem into a different domain, solving the problem, and then reversing the transformation. The other thing mathematical transforms allow us to do in some cases is they allow us to visualize things about data or problems that we might otherwise not be able to visualize or see in quite the same way. So it's a very useful area. Now, what we're going to be talking about are integral transforms, and many of you, most of you, all of you, I'm sure, have heard of the Laplace transform, the Fourier transform, some of you probably the wavelet transform. All of those are integral transforms, and basically an integral transform is taken using the following mathematical equation, where k is some function, and we're going to go ahead and let it be a function of, f is some function, and we're going to go ahead and let it be a function of time in this case. And then k is known as our kernel function, and u is known as our transform variable. So notice that we're taking this function f of t, which is our data set or our function that describes our physical behavior, and we're multiplying it by k of t and u and integrating it across some range over time. So time, after this integral is accomplished, will cease to be a variable, and our new variable will be u, our transform variable. So in many ways, this integral transform can be viewed almost like a filtering technique, where the output of the transform operation gives us an idea of the content of the kernel function at a given value of u that was present in our original function f of t. So if we use the Fourier transform as an example, omega, the transform variable, is the frequency. And if you look at a particular value of omega, the Fourier transform gives you an idea of the amount of that frequency that was present in your original signal. So sometimes an inverse transform exists, involving an inverse kernel function, sometimes but not always. So in this case, we would take our transformed function and integrate it over u multiplied by the inverse kernel function, and we would get our function of time back. Now, a kernel is said to be symmetric if the variables u and t can be interchanged to take the inverse transform without changing the function k. Integral transforms, as we said before, are useful because they sometimes map problems into an easier space so that we can do a solution and then inverse map back to our original space. So there are a wide range of integral transforms. The Laplace and Fourier transforms are two well-known transforms in electrical and computer engineering, but there are others as well with specific applications. The point of this lecture is just to give you an overview of some of transforms in general, along with a couple of specifics. And then when we have our in-class meetings or with follow-up online lectures, depending on whether you're taking the hybrid or the distance version of this class, we'll go over the specific Laplace and Fourier transforms as well as a couple of other examples in more detail. So here is a table of common integral transforms. This is if you go to Wikipedia and look up integral transforms, this is the table that will come up, and it's a very nice summary. And you can see the first line here is the common Fourier transform. There are less commonly a Fourier sine transform and a Fourier cosine transform. Notice these are interesting because they don't run from negative infinity to infinity, they run from 0 to infinity. They have the advantage of being real valued, but they have the disadvantage of yielding incomplete information about a signal. The Hartley transform is sort of a combination of the Fourier sine and Fourier cosine. It does run from negative infinity to infinity. And then we'll skip down. You can see the Laplace transform. There is a two-sided Laplace transform that's never used because as a general rule we use the Laplace transform to represent initial value problems. So we're typically interested only in the range running from 0 to infinity, e to the minus ut is our transform variable, and u in the Laplace transform is a complex frequency, as opposed to u in the Fourier transform, which is a real number. There are some others. The Hankel transform uses Bessel functions. The Abel transform is one that's used in optics. The Hilbert transform is used in signal processing. So as you can see, there are several of these integral transforms. So just looking at a couple of specific ones, the Fourier transform uses an exponential with an imaginary exponent as a kernel function, and the transform variable represents frequency space when the input variable represents time. For those of you who are interested in image processing or image analysis, the Fourier transform can also be done spatially. In that case, it's a two-dimensional problem with an x and a y if you're representing a two-dimensional figure. And the transform output is also two-dimensional and will indicate spatial frequencies. So, for example, sharp edges would be a high spatial frequency content, while slow gradations would be a low spatial frequency content. This is the equation for the Fourier transform, where zeta here is a real number. In electrical engineering, the most common thing is to use frequency space. So we would have e to the minus j omega t for our transform kernel function. F of t is our function. This 1 over 2 pi is included here to normalize the units, because we're transforming into radians per second as opposed to inverse seconds. So this is just a couple of example figures that show a signal and its Fourier transform. The Fourier transform is symmetric about time, or the signal is symmetric about time. The integral always runs from negative infinity to infinity. Here's the real and imaginary parts of the transform and the kernel function. So the Fourier transform application is used in signal processing and in image processing. In the time domain, if the signal is in the time domain, Fourier analysis determines the spectral content of the signals and is used in filter design as well as in numerous other applications. In the spatial domain, Fourier analysis can be used in edge detection, denoising, compression, and actually also in spatial filtering. The Hartley transform was actually developed to provide a real number alternative to the Fourier transform while still finding frequency content within a function. So the advantage is here, and I don't know, to be honest, if it's an advantage or not, but the advantage is you're using a sinusoidal and cosinusoidal or trigonometric functions as opposed to exponential functions. So the advantage here is you get only real frequencies. You don't get confusing things like negative frequency that come out of this. And you're not dealing with e to the j omega t, which is not a real valued function. You're dealing with sine and cosine. The disadvantage is you have transcendental equations and trigonometric integrals, which can be sometimes difficult to do. We find those on tables now, or put them into MathCAD or some kind of math processing toolbox, and that's helpful and makes it easier than it used to be. But the Hartley transform is not that widely used. The Hartley transform is related to the Fourier transform, so F here represents Fourier transform, H represents Hartley transform, and here's how to get the Fourier transform out of the Hartley transform. The Hankel transform, as we mentioned before, uses Bessel functions as kernel functions, so this can be sometimes useful in modeling things like electromagnetic fields or certain concepts in physics that that have a Bessel function geometry. And here basically we mention that where these are the Bessel functions. There's the solution to this differential equation. If alpha is an integer, then the Bessel functions end up being the solution to Laplace's equation in cylindrical coordinates. If it's an integer plus a half, then they're the solution to Laplace's equation in spherical coordinates. And obviously, as we discussed before, one of the most famous applications of that is that Bessel functions represent solutions to waves in a cylindrical waveguide. Here's a plot of the Bessel functions that I believe we showed in a previous lecture when we talked about differential equations. The Hankel transform, there's a table given on the next slide that shows some common transform pairs. Its main application is in computer tomography image reconstruction in polar coordinates, so it's used in image processing. Here are some transform pairs for the Hankel transform. Here's the original function. In this case, it's given as a function of r, radial geometry, and then the output function is what's referred to as k-space, which is like a frequency as a sort of an inverse radial coordinate system. The Abel transform is used in problems where you have axial or spherical symmetry. It represents the projection of an axially symmetric thin emission spectrum. So like photoelectron emission, it's primarily a physics problem, a physics application. The Hilbert transform, once again, is used in signal processing and filtering. If we have time this semester, we'll discuss the Hilbert transform in a little more detail because it does allow you to obtain what's known as an analytic function when you need such in the signal processing. It'll shift the function, it'll shift the phase of the function by 90 degrees. So when you have a Fourier transform and you take the Fourier transform, you get negative frequencies because the Fourier transform is a complex number. So if you have measurement where you're actually measuring a spectrum, you don't get the negative frequencies out of the spectrum. So you can't really do filtering in quite the right way if you're trying to filter in the frequency domain if you only have real valued numbers. So what the Hilbert transform allows you to do is it allows you to come up with a transform that basically will create a complex function, and then that will give you real values when you take your inverse Fourier transform. So that's kind of a common thing. So there are some other applications. Hilbert spaces are n-dimensional vector spaces. They are used in machine learning. You can have a set of inputs and outputs and predict an output given a new input using linear regression, which we'll talk about a little bit later in this semester. One of the problems with linear regression is it's possible to have, when you have multiple dimensional vector spaces, it's possible to have more than one local minima solution, so you can get multiple linear regression solutions. So the Hilbert function is used to perform nonlinear regressions so that you can get better fits. The wavelet transform is another thing we'll discuss in more detail later. Wavelet functions are orthonormal functions, and we'll define that also in detail later. They basically make up a Hilbert space, and they're used, basically they're comprised of a wavelet function and a scaling vector, and so they're used to model things in time domain signals that occur in unique specific places in time. So the wavelet transform gives you both a time and space kind of scale that, or a time and frequency kind of scale. So we'll discuss wavelets in a separate lecture. Here are some of the specifics on the wavelet transform. At this point, I just want to show the transform equation. You notice that in the equation there's a variable b and a variable a when we look at our wavelet function psi. So we actually have two transform variables, a and b, where a is sort of acting like a zoom lens and b is a time shift. So the b variable is sort of acting like a convolution variable, and the a variable is acting like a scaling variable. So we will go through in a separate lecture a more detailed lecture on the wavelet transform and why it's useful. But it's important first to discuss the Fourier transform, review the Fourier transform briefly. So this is going to constitute the end of this introductory lecture to different transforms. Specifically in this class, we will cover in more detail the Laplace transform, the Fourier transform, and the wavelet transform. And then if time permits, we'll look a little bit more at the Hilbert transform in Hilbert spaces.